Layout is the process of determining the location of objects in consideration of their intended placement. The intended placement of objects is described by the architect using construction plans. Construction plans describe the completed work, including all objects and materials which are present in the finished state. This means that throughout the process of construction, layout must be performed in consideration of the intended completed project. In addition to understanding the intended finished work, when performing layout, it is necessary to understand the objects being located, including their functional purposes. Objects are described by product manufacturers using product documentation. Product documentation includes installation instructions, drawings, and more. To the extent necessary for products to be made useful, product documentation explains the internal arrangement of an object's components, proper installation procedures, the conditions that surround the object when it has been installed, and the object's operable functionality, including limitations on that functionality. D&G has developed standards for the performance of each type of work the company performs. D&G's standards identify the features embodied in its finished work, including the acceptable amount of deviation from intended placement and expected functionality. Refer to D&G's work type specific resources before performing layout. Units such as liters, pounds, inches, and centimeters are standards of comparison for measurements. When we buy a 2-liter bottle of a soft drink, we expect that the volume of the drink was measured so that it's 2 times larger than the volume that everyone agrees to be 1 liter. Without units, a number can be meaningless. Sometimes we use units that are fractions or multiples of a base unit. Ice cream is sold in pints, quarts, and gallons. The standard unit of length in both the SI and original metric systems is the meter. A meter was originally specified as 1/10,000,000th of the distance from the North Pole to the equator. It's now defined as the distance light travels in a vacuum in 1/299,792,458th of a second. Since the International Yard and Pound Agreement of 1959, 1 foot is defined as 0.3048 meters exactly. In customary and imperial units, 1 foot comprises 12 inches and 1 yard comprises 3 feet. Altitude is the height of an object relative to a reference. The most commonly associated reference is sea level. In the absence of any reference, the concept of altitude has an uncertain meaning, if it has any meaning at all. Similar to the Earth's oceans, the Earth's gravity provides a convenient reference for measuring orientation. Plumb and level references describe orientation with respect to the direction of gravity's force. Orientation which is exactly the same direction as gravity's force is said to be plumb. The orientation which is perpendicular to the direction of gravity's force is said to be level. Other terms used to describe orientations that are perpendicular to each other include square, right angle, and 90 degrees. The plumb and level orientations provide convenient references, which can be easily measured using commonly available construction tools such as lasers, levels, and plumb bobs. By combining these orientations with dimensioned units of length, we can project an imaginary Cartesian coordinate system. A Cartesian coordinate system provides a means for describing the spatial orientation of points. Triangles are simple, 3-sided shapes. You might remember studying triangles in geometry. Perhaps you also remember the trigonometric functions which allow us to calculate a triangle's angles from the lengths of its sides. You probably don't remember the approximation formula. Maybe you remember the different triangle congruency theorems, which allow us to calculate all of the triangle's sides and angles when we know only a few of their values. Those theorems and formulas are not particularly important when it comes to collecting measurements. What is important is that we understand which measurements to collect. So which measurements should you collect? Well, when you combine the discussion of plumb and level reference lines with a discussion of triangles, you can begin to appreciate the significant amount of information that we can interpret from measured values. In order for us to really drive it home, let's take a look at a four-sided shape where we know the lengths of all four sides. We don't know anything about the angles. The same is true when we have 5 connected sides. Just simply knowing their dimension tells us nothing about the angles between those dimensions or the relationships of those points to each other in space. But this isn't true for triangles. Here we have an equilateral triangle, all 3 sides the same length. If we keep 2 of the sides the same length and we allow one to vary, then we can show an animation of the triangle rotating. Notice that one of the dimensions is changing in size. You can't have 3 connected dimensions and different angles. If we know the dimensions of 3 sides, then we know the angles between those sides. So in this way, triangles provide us with valuable information that describes the spatial orientation of points. Any of their angles can be calculated when the length of the sides is known. This means that they can be used to record the size, shape, and angles of other, more complex shapes. This feature is especially useful when measurements are taken on a horizontal plane where plumb and level reference lines are not available, such as when measuring countertops. As if triangles weren't already useful enough, the 3-4-5 triangle provides a convenient way to lay out square corners. A 3-4-5 right triangle is a triangle whose side lengths are in the ratio of 3 to 4 to 5. In other words, a 3-4-5 triangle has the ratio of the sides in whole numbers called Pythagorean triples. This means that a triangle which measures 30 inches by 40 inches by 50 inches has one square corner. So how do we use this? We can lay out the locations of walls perpendicular to each other. We can use the dimensions of a 3-4-5 triangle to find a line that's perpendicular to an original line. We do this by measuring out a radius of 40 inches from the end of our line. We measure back along the length of our line 30 inches, and from that point, 30 inches from the end, we'll measure out a 50-inch radius. Where the 40 and 50-inch radii cross, that's going to give us a point along the line that's perpendicular to our original line. It's difficult to record the shape of curves with a tape measure. However, the radius is the only piece of information necessary to describe the shape of a curved path. The radius is a straight line from the center to the curved path or circumference. While the exact center is not normally easy to locate, the dimension of the radius can also be calculated from other measurements which are easy to take. The chord length, C, in the figure is normally easy to measure. Usually the segment height, H, in the figure is taken to be the difference between other height measurements. Note that H must be measured at the center of line C. The dimensions of C and H can be used to calculate the radius of any curve. When you use these dimensions, you must be careful to measure H as precisely as possible. Errors in the measurement of H can drastically change the value of the radius, especially when the values of h and c are small. It's also important to understand that the shape of the curve you're measuring can vary along its length. In order to minimize the possibility that local variations in the surface of the curve will lead to the determination of the radius incorrectly, it's a best practice to collect more than one CH measurement pair. You can see that geometry of any complexity can be described by the dimensions of radii, triangles, and the indication of how these measurements are connected to each other. So how can we use this information? Collect the measurements. When you do, we'll be able to use them to recreate the geometry that you measured in a CAD program. Measuring tools often have graduations which correspond to units. Suppose we use such a tool to measure an object as shown. Clearly, in this example, and is most often the case, the size of the object being measured does not correspond exactly to graduated markings on the measuring tool. Whenever this happens, it's important that we report the measurement to the nearest graduation marking. In this case, 12 and 3/16 and 12 and a quarter are both acceptable because they're both within the standard tolerance for measurement error, which at Dorian class we take to be a 1/16 of an inch. Construction work is always required to conform to some level of precision. Construction work is always allowed to be imprecise within the limitations set by industry standards. Industry standards are typically published by industry groups. Industry groups are made up of individual companies that are affiliated by the type of products and services that their firms provide. The standards are developed and agreed upon by the various companies participating in their development. D&G identifies the industry's allowable tolerances in work-type specific company standards. This is a scale drawing of a tape measure just to demonstrate the importance of reading a tape measurement straight on. This is 30 degrees to the left and 30 degrees to the right. You can see that the measurement apparently changes by a 1/16 of an inch. The object being measured falls between two 1/16 inch graduation markings. In this case, the object is 12 and 7/32. 7/32 is 3.5 1/16 of an inch. At Dorian class services, we don't record measurements to the nearest 32nd of an inch, so the correct way to report this measurement would be by rounding it to the nearest 1/16 of an inch. So this dimension would be reported as 12 and 3/16 or 12 and 1/4. If the measurement is taken from an angle, then the correct dimension is 12 and 1/4 or 12 and 5/16. No, that's not what we want. We need to do our best to read the tape measure straight on. In the same way that construction work normally deviates some amount from its expected dimensions, manufactured products normally deviate some amount from their expected dimensions. Just as the construction industry has established standards, manufacturing industries have published standards for the inherent deviation of manufactured sizes from ordered sizes. Manufactured products often differ from expected or ordered sizes as the result of both measurement and machine tolerances. Machines themselves can be imprecise, which is part of the reason that we need to allow tolerance for manufacturing error. Operable parts of machines can have play in their dimensions, which results in some uncertainty as to the position of the materials they're used to manufacture. Machinery can also have more than one axis. Compound miter saws provide an example. While each axis of a machine might be adjusted independently, it is important to recognize that manufacturing equipment is not always capable of perfect precision or accuracy. The company's standard for accuracy of metal parts, which it cuts to size, is plus or minus 1/16 of an inch. This tolerance allows for errors in the measurement of cut sizes and tolerances required by the company's equipment. However, other manufacturers may require more or less tolerance. Error is contained in every measurement. Therefore, it is necessary to understand how to correctly anticipate the amount of error which is likely. As discussed, the company anticipates a maximum measurement error of 1/16 of an inch. The company also anticipates a maximum deviation of 1/16 of an inch in the dimensions of metal parts which it has cut to size. While it might be easy for an individual to perform work at higher than 1/16 of an inch tolerance, when different people are responsible for different aspects of the company's production, it's likely that results will deviate by more than 1/16 of an inch. The fact that other people are likely to perform different aspects of production should not be discounted when performing layout. Allowing 3/64 for measurement error and 1/16 for error in manufactured dimensions, we should anticipate that a total error of 7/64 is always possible. This amount is slightly less than 1/8 of an inch. The company, therefore, should not guarantee the precision of its work beyond 1/8 of an inch because its precision will normally vary by some amount. The total amount of error which is possible can be much larger than 7/64. Consider a product which is assembled from multiple panels. Suppose that the manufacturing tolerance allowed for the width of each panel is 1/16 of an inch. The total error in the assembled product's width, if all panel widths are manufactured to within acceptable tolerance, could be as much as 1/4 inch in only 4 panels. When you consider that the measured dimension could vary by 3/64 of an inch, and that 4 panels could vary by 1/4 inch from the ordered dimension, the assembled product could be as much as 1/4 inch plus 3/64 different from what might otherwise have been intended by the architect's drawings. When the actual size of a product is different from the intended design, does that make the product the wrong size? No. The size of the product is either within an acceptable range of possible sizes, or the size of the product is outside of the range of possible sizes. It is important to recognize that the intended design is constructed as precisely as possible using imprecise methods. Errors can accumulate, which means that they can combine to produce an even larger error. But that does not mean errors always accumulate. Just like flipping a coin enough will lead to an even number of heads and tails results, when errors are equally likely to be more or less precise than the expected dimension, the total amount of error expected to accumulate in the result is 0. However, the probability of accumulating error is much higher when the number of dimensions is small. The probability that 2 errors work to offset one another is 50%. The probability that 2 errors accumulate to produce a larger error is also 50%. As the number of dimensions increases, the actual probability that all dimensions accumulate declines. In a perfect world, there is an equal chance that all errors will be more or less than the expected dimension. Perhaps an operator believes it's okay to locate a clamp once and proceed to cut 100 pieces of material the same size, and they don't check any of the cut dimensions. Sometimes, after checking the dimension of the first cut, An operator might foolishly proceed to cut 99 more pieces of material a 32nd of an inch too large or too small because 1/16th of an inch is the allowable tolerance. We can't account for errors in the competent performance of our own responsibilities, but that's not the type of error that we're discussing. We're interested in accounting for the amount of error which should reasonably be expected. Because our focus is on this type of error, we assume that it occurs equally in both directions. Using a window as an example, suppose that we measure the opening and manufacture the frame. We expect the total amount of error to be as much as 3/64 from the initial measurement plus a 16th for each panel. If the frame has 4 panels, the size of its width could be as much as 3/64 plus a 16th, a 16th, a 16th, and a 16th, or 3/64 plus a quarter, different from the intended size. This result may be extreme, but all 5 errors accumulate 6.25% of the time, a little bit more than 1 in 20. Disregarding the measurement of the opening size, errors in 4-panel frames accumulate 12.5% of the time. If only 1/4 inch is allowed for shimming, as many as 6.25% of 4-panel frames may need to be modified to fit their openings when all the panels are fabricated within acceptable tolerances. Shim spaces and caulk joints are an important means for accommodating dimensional errors in measurements in manufactured products. Properly allowing for shim spaces and caulk joints reduces the likelihood of modifying product sizes in the field.